All right, today we are diving into one of the coolest, most essential tricks that your computer, my computer, every modern computer uses. It's all about how they handle memory using these, well, secret maps.
So let me ask you something. You ever check your computer, right? You see you've got tons of free memory, gigabytes of it, but then you try to launch a big program, and nope, the computer just refuses. It makes no sense, does it? Well, there's a very good reason for that, and we're going to figure it out.
Okay, so to get to the bottom of that mystery, we first have to talk about a big problem your computer faces every single second: wasted space.
Okay, just imagine your computer's RAM is like one long bookshelf. When you open a program, your computer finds a big enough empty spot on that shelf and just plops the program right there. You close the program? Great, that spot is now empty again. Seems simple, right?
But here's where it gets messy. After you've opened and closed a bunch of different programs of all different sizes, your shelf starts to look kind of like Swiss cheese. You've got these little gaps everywhere. Now, along comes a huge new program that wants to load. And you know, if you add up all those little empty spots, there's plenty of total space. But here's the kicker: none of the individual gaps are big enough to hold the whole thing in one piece. So, denied. The program can't fit.
And this super frustrating problem, it actually has a name. It's called external fragmentation. Yeah, that's the technical term for having all the space you need, but it's just chopped up into useless little bits. It's a massive, massive waste. So, what do? How on earth can we use all that wasted space? Well, this is where some very clever people came up with a beautiful, elegant solution, and it's called paging. Let's look at the difference here. The old way, on the left, meant a program was this one big, solid thing. It had to find one big, solid empty space. Super inefficient. But the new way, paging, is totally different. The genius idea was, what if we just stop trying to keep the program together? What if we chop it up and just stuff the pieces into whatever empty slots we can find? And that's pretty much exactly how it works. Step 1. The operating system takes your program and slices it into these small, perfectly equal-sized chunks. We call those pages. Step 2. It does the exact same thing to your physical RAM, dividing it into slots of the exact same size, and we call those frames. So what's the result? Now, any page from your program can fit perfectly into any empty frame in memory. They don't have to be neighbors anymore. They can be scattered all over the place. And this is the golden rule. You have to remember this one. The size of a page is always exactly equal to the size of a frame. They're a perfect match. Think of it like a Lego brick. One page fits perfectly into one frame. No gaps, no leftovers.
Okay, but wait a second. This creates a whole new puzzle, right? If the program's pieces are scattered all over the place, how in the world does the CPU find anything? The CPU is simple-minded. It thinks a program is one long, continuous thing. Well, this is where the real magic happens. This is the address translation trick.
See, the computer now has to juggle two different kinds of addresses. On the left, you've got the logical address. This is the CPU's view of the world. It's kind of like a fantasy land where the program is all neat and tidy and in one piece. The CPU might say, hey, I need byte number 3. But on the right, you have the physical address. This is the messy reality of where things actually are in RAM. That byte number 3 the CPU wanted? In reality, it might be way over at location number 9. So, how do we bridge that gap between the fantasy and the reality? We use that special map we talked about at the beginning, and it's called a page table. Every single program running on your computer has one of these. And this is what it looks like. It's not complicated at all, really. It's just a simple lookup chart. The left side lists the program's pages, page 0, page 1, and so on. The right side tells you which physical frame in RAM that page is actually sitting in. So if the CPU says, I need something from page 1, the page table just goes, oh yeah, no problem, you'll find that over in frame 4. Simple as that.
So let's walk through the whole thing step by step. First, the CPU asks for something. It generates a logical address. The system immediately splits that address into two pieces, the page number and an offset, which is just the position inside that page. Then, it uses that page number to look up the real location in the page table, finding the corresponding frame number. It takes that real frame number, slaps the original offset onto the end of it, and boom, you have the true physical address. Finally, it goes to that exact spot in RAM and gets the data. And this whole translation process, it happens billions of times a second. It's unbelievably fast.
Okay, I know that was a little abstract with all the pages and frames, so let's use a real concrete example to see how the numbers actually crunch. All right, let's pretend we have a simple system where the logical address, that's the one the CPU uses, remember, is just 7 bits long. Now that number tells us how big the program thinks it is from the CPU's point of view. So if we have 7 bits, what does that mean? Well, 2 to the power of 7 is 128. That means the CPU can imagine an address space with 128 different spots, from 0 all the way to 127. To the CPU, it's just a simple little program.
Now, this slide is where it gets really cool. We see how that address is split up. The logical address is part page number, part offset, and the physical address is part frame number, part offset. But look closely, the offset part, it's exactly the same in both. It just gets copied straight over, and that's the whole secret. The page itself can be moved anywhere in memory, but a byte's position inside its page never, ever changes.
So, we've covered the problem, the solution, the whole crazy mechanism. But let's take a step back. Why does any of this matter? Why is this one clever trick so fundamental to, every single computer, phone, and tablet we use? Well, for a few huge reasons. First, and most obviously, it totally gets rid of external fragmentation. We can now use every single drop of available memory. Second, this is what makes modern multitasking possible. It lets dozens of programs, with all their scattered pieces, share memory at the same time without tripping over each other. And finally, it just makes the operating system's job so much easier. No more hunting for a perfect-sized block of memory. Any empty frame works.
So, paging is this incredible system for mastering the physical RAM you have. But it brings up one last really interesting question. What happens when a program is so massive that it wouldn't even fit in RAM if you used every single last byte? Well, that's where this whole secret map idea leads to an even more clever trick. But that is a story for another time.